So one thing to remember is that all maps are scale representations of reality. So what happens when there's no obvious scale? So there's a few different things that we could do to figure out scale of a map. We can use known features, so we can reference features such as football fields, tennis courts, or baseball diamonds. There's the use of line of latitude and longitude. So 1 degree of latitude is 69.2 miles on average. Or we can do a map comparison. So we use another map of the same area with similar distinctive features. So one might come across a map or aerial photo with an unknown scale. In this situation, one uses recognizable features of known size or refer to another map that includes the same extent and has a known scale. For example, suppose someone acquired a photograph of an aerial image depicting a city. One thing that you can do is look for a football field. Since a football field has a known length of 100 yards, you can use the length of the field to determine scale. So the football field represents 100 yards on the ground and thus used as the denominator of the scale ratio. Suppose measuring the football field on the image using a ruler resulted in the length of 1 inch. This number would provide one with a numerator. Right away, one could determine the scale verbally, 1 inch to 100 yards. Likewise, one could draw a graphic scale using 1-inch increments to create a scale bar. You could also determine the representative fraction by converting yards to inches and simplifying the fraction. You can also use baseball diamonds, tennis courts, and other sports facilities, which are generally all a specific size and thus used in this manner. There may be a time when one needs to determine scale using geographic coordinates such as latitude and longitude. To determine the numerator of the scale ratio, one would measure the distance between 2 lines of longitude or two lines of latitude on the map. Next, one would have to convert latitude or longitude degrees into other units of measure such as miles or kilometers to determine the denominator of the scale ratio. To accomplish this, one has to know the length of a degree of longitude or the length of the degree of latitude. Because a geographic reference system uses an ellipsoid base, distances between longitude and latitude are not consistent. They depend upon the location and the reference ellipsoid used. In most cases, one may not have a sports field handy and will have to determine scale using a known source. If we look at the map on the slide here, we see a Let's Walk audio tour. Obviously, this map is not very detailed and there's no scale. There's not even a north arrow. To determine the scale of the photo, you could use a map of the same area with a known scale. Measuring the distance between 2 points on the audio tour map, such as 2 street intersections, would give one the numerator of the scale ratio. Measuring the same 2 points on the reference map and using the map scale to determine the distance on the ground would give one the denominator. Then, as in the previous example, one can use conversions to generate a representative fraction, a verbal scale, and a scale bar. So let's do a little bit more scale practice. So again, here are some unit conversions. So let's try to determine the scale of this thematic map. So what we need to do is define a reference map with similar distinctive features with a known scale. So on a reference map, the scale is 1.5 inches equals a half mile. The airfield on the reference map measures 3 inches. On the tourist map, the airfield is 5 inches long. So what is the scale of the tourist map? So the first thing we want to do is plug in the pieces that we know. So we know that an inch and a half equals a half mile on the reference map, and we know that 3 inches is the map distance. So we're trying to find the ground distance. We want to convert our units to the smallest unit, so we'll convert miles to inches. And then we'll want to cross multiply to bring x to the numerator. And then we will divide to isolate x and leave as in inches for the next part. So now we'll be able to figure out the ground for the tourist map. So here we have our representative fraction and then our scale formula. So we have the unknown map and the ground distance. So we know on the tourist map, the airfield is 5 inches long, and we're going to put that over ground, which we just calculated for in the known map, and we got 63,360 inches. And then we'll want to simplify. And so we get a representative fraction for this tourist map of 1 unit to 12,672 units. So what if we wanted to create a scale bar for the tourist map? We now know the scale of the tourist map is 1 unit to 12,672 units. So we want to know how long would a scale bar be for 500 feet. So here we have our general scale formula. We have our representative fraction and map to ground. So let's plug in the pieces that we know. So we know that our scale is 1 unit to 12,672 units. And we know that we want our ground distance to be 500 feet. So we need to now solve for our map distance. So first of all, we need to convert the units to inches. We want to isolate x, and then we want to simplify. And so when you're simplifying, you're going to divide 6,000 by 12,672, which gives you 0.47 inches. So we know that 0.47 inches is going to, on the map, is going to equal 500 feet on the ground. All right, so let's look at measuring vertical distances. We will be needing to use the Pythagorean theorem. A squared plus b squared equals c squared. So we have our map distance, which is the run, and our elevation change, which is the rise, and then our actual distance. So how do we find b? On topographic maps, there's a graphical representation of the Earth's surface. There's the use of contour lines to represent elevation, and it shows natural man-made features as well. So you can find elevation using contour lines on topographic maps. Another way to find elevation is to use benchmarks and spot elevation. So you have surveyed in benchmarks, and then you have your spot elevation points. So here are your 2 benchmarks, and then your spot elevation, and you could use those to triangulate. So let's do the math. So we know that our map distance is 500 feet, and we have our 2 benchmarks. So we have 3,263 feet, and then we have a benchmark elevation here of 3,227, and so you want to find the difference between those 2 points, and then you will solve for C. So you have your 500 feet for A, and you have 36, which is the difference between those 2 benchmarks for B, and then you have C. So you need to find what 500 square is plus 36 squared, and that is going to equal C squared. And once you have that calculation done, you get 251,296 equals C squared. And so you will then need to find the square root of both sides to come up with your final answer. So you get an actual distance between the ground and the elevation change, which is going to be 501.3 feet. So let's look at contour lines. So contour lines connect points of equal elevation. The contour interval depends on topography, whether it's so that means steep slopes equals larger intervals. And the interval is constant for the entire map. So when you look at a topographic map, look at it as if you're looking at a cross section of a shape. So if you were to have a mountain that has these different elevation changes and you were to slice it and look at it from on top, you would get your contour lines for a topographic map. So when you're looking or when you're reading contour lines on a map, one thing to look at and to notice is when you see contour lines really spread apart, you have your gentle slopes. And then when they're really close together, you have cliffs. Hills will have a center and go down. And then you have your saddle and valley characteristics as well.